Welcome to the deep dive. Today we are taking a look at, well, one of the fastest moving fields out there, the future of cognitive science.
Right.
And this isn't just psychology or just, computer science. It's this incredible collision point. We're talking psychology, neuroscience, linguistics, philosophy, anthropology, and computer science all coming together.
And that collision has really pushed the field to
Yeah.
this crucial pivot point. I mean, the source material we dug into really lays out three big forces driving everything.
Okay, what are they?
First, you've got these technological leaps that are just unprecedented.
Mm-hmm.
Second, there are these huge ethical questions we just can't put off anymore.
Mm.
And third, there's a real need to apply all this knowledge to, solve actual real-world problems.
So our mission for this deep dive is to cut right through all that complexity. We're going to isolate and really unpack the top three theoretical frameworks that are, well, they're redefining how we understand the human mind right now.
Exactly. Think of this as your intellectual shortcut. We're hitting the three biggest shifts. The computational revolution, a really interesting idea called predictive processing, and then this radical approach called the 4E cognition movement.
All right, let's jump in. Okay, let's start with the computational revolution. Now, for decades, cognitive science used the computer mostly as a metaphor, right? The brain is like a computer.
Yeah, processing symbols, running programs, that kind of thing.
But the material we're looking at says we've blown past that. We've moved from just a metaphor to a genuine theoretical tool. What does that actually look like?
It looks like artificial neural networks, ANNs, and the large language models, or LLMs, that everyone's talking about.
Okay.
The big shift is that these systems aren't just stand-ins anymore. They're so complex, and their design is so, loosely inspired by biology, that they become these amazing laboratories for testing theories about the mind.
So you can actually watch them learn.
Pretty much.
Yeah.
If we want to understand how a brain takes a ton of messy data and finds a pattern, we can actually build an ANN, train it, and literally observe how it does that.
So the model itself becomes part of the science. It can create behaviors that we didn't explicitly program into it. That's a huge jump.
Precisely. And that's where you get these really profound theoretical questions. I mean, when these systems start doing things we thought were uniquely human,
Like what?
like generating completely new text that makes sense, or recognizing incredibly subtle patterns, or even creating original art, it just forces you to step back and ask some really fundamental questions.
Questions about intelligence itself. Is it just that they can handle way more data than us?
It's more than the scale. I think it's the coherence, the current creativity that really challenges us.
Right.
Before this, we kind of put creativity and real understanding up on this pedestal. There were these like mystical human things that you couldn't just reduce to code. But now we have models producing art or poetry that is, sometimes indistinguishable from something a person would create.
But the critics always say it's just mimicry, right? It's a statistical trick. If the machine doesn't feel anything, can you really call it intelligent?
And that is the absolute core of the debate now. The question isn't so much, can a machine do X or Y anymore? It's if a machine can perform a task at a human level, say, writing a poem that actually moves you,
Yeah.
does the fact that it doesn't have a subjective experience, does that invalidate the output?
I see.
So cognitive science has to figure out if intelligence is about observable performance or if it's about some kind of internal subjective understanding.
Yeah.
It makes us look in the mirror and ask if our own thinking is, at its root, just a much, much more complex form of pattern recognition.
Let me try to make this really concrete for you. So imagine you're an art history professor. An AI generates a piece of abstract art. You look at it, you analyze its technique, its emotional impact, and you decide it's a masterpiece. Then someone tells you an algorithm made it. That moment, that reveal, it forces you to completely reevaluate what creativity even is. Maybe it's not some divine spark. Maybe it's just the incredibly complex processing of a giant data set of all the art that came before it. That's the computational revolution in action.
Okay, so let's pivot now. We're moving from the tech revolution happening outside the skull to an equally radical idea about what's happening inside the skull.
Right.
Predictive processing.
Yes, and this one is, it's a really big deal because it's a complete reframing of what the brain's main job is. And it's getting a ton of attention because it might just be a unifying theory for almost everything the brain does.
Unifying is a big word in science.
It is. The old view of the brain was pretty passive. Information comes in from your senses, the brain processes it, and then you react. Predictive processing just flips that whole idea on its head.
So the brain is a fortune teller, basically. It's not just a camera recording the world. It's constantly making guesses about the future. That's a great way to put it. At its core, the brain is always generating predictions about the sensory input it expects to get based on everything it's learned before. It's building a model of the world constantly. And then perception learning. It's all driven by what are called prediction errors.
Prediction errors. So the moments when reality doesn't match the brain's guess, what happens then? How does that error signal actually drive anything?
That error is the most important signal in the whole system. If your prediction matches what your senses tell you, great. The system is efficient. No news is good news.
Okay.
But if there's a mismatch, a prediction error, the brain has two options. It can update its model of the world, that's basically learning or perception, or it can trigger an action to change the world so that it does match the prediction.
So action, perception, and learning are all just different ways of dealing with the same thing, minimizing surprise.
Exactly, minimizing prediction error. It's this incredible simplification. It brings so many different mental functions under one single principle.
And that's why it's such a strong candidate for a unifying theory.
That's it. The explanatory reach is just huge. Think about just picking up a cup of coffee. Your brain is predicting the sensory consequences, how the cup will feel, how your hand will land. If the feeling isn't what it predicted, you instantly correct the movement. That's error minimization. And the theory suggests that same basic process applies to everything from learning a language to deciding which way to walk home.
Let's make this really vivid using the examples from the research. First, just how powerful our predictions are. Think about optical illusions.
Yeah, those are perfect examples.
When you look at certain illusions, your brain's prediction, its deep-seated expectation about how shapes and shadows are supposed to work, it can completely override the raw data coming in from your eyes. The prediction literally causes you to see something that isn't physically there.
It's just compelling evidence that we don't see reality directly. We see our brain's best guess of reality. And that guess is usually really good, but sometimes it fails spectacularly.
And the second example is so important for mental health. If the brain's job is to minimize error, what happens when that prediction machine breaks down? The research points to conditions like schizophrenia and autism.
Right.
With schizophrenia, one hypothesis is that the brain can't properly weigh incoming sensory data against its own internal predictions. It over-prioritizes its own model, leading to hallucinations or delusions.
And with autism, some researchers think it might be the opposite problem, an atypical weighting of prediction errors. Maybe the brain is too sensitive to error, treating every little sensory input as a massive surprise. That could lead to sensory overload and make it hard to build up stable general models of how the world works.
And the potential to explain both normal perception and mental health conditions with one single framework. That's why this is such a huge deal for the future of the field.
Yeah, absolutely.
So if the computational revolution is about processing power and predictive processing is about what's happening inside the brain, our third big idea asks a more fundamental question. Where does thinking even happen? This is the 4E cognition movement.
And this movement is really the intellectual counter-argument to that traditional idea of the mind being just software running on the brain.
Right. Mindware.
Exactly. The 4E framework says cognition isn't locked up inside your skull. It is fundamentally embodied, embedded, extended, and inactive.
That's a lot to unpack. Let's take the first two, embodied and embedded.
Okay, so embodied cognition is the idea that the specific kind of body you have, 2 arms, 2 legs, you stand upright, doesn't just influence what you think about, it shapes how you think. Simple concepts like up and down only make sense because of our physical sensory experience with gravity. Our body provides the very structure for our thoughts.
And embedded cognition, that sounds like it's all about context.
It is. It's the idea that our thinking is always situated in and supported by our environment.
Yeah.
You know, when you're trying to solve a puzzle, you don't just do it in your head. You move the pieces around, you jot down notes. Your environment becomes a kind of external hard drive and processor.
Okay, the next two are where it gets even weirder for our sense of self. Extended and inactive cognition.
Extended cognition is probably the most disruptive idea of the 4. It argues that some external tools actually become part of your cognitive process. The boundary of your mind literally extends out into the world.
So the tool isn't just a helper, it's an actual active part of your thinking process. What's the classic example for that?
The classic example is your smartphone. When you use it to navigate, or when its calendar reliably stores all your appointments for you. That information storage and retrieval process is functionally no different from memory inside your brain.
What?
The cognitive task is distributed across your brain, your body, and the phone itself.
And the last one, inactive cognition.
And activism says that thinking isn't just about processing information. It emerges from our active, goal-directed interaction with the world. You don't just passively see the world and then think about it. You actively build your experience by moving through and acting on the world. Thinking is a form of doing.
So the big conflict here is pretty clear. The 4E view says traditional cognitive science made a huge mistake by only looking at the computation happening inside the head and ignoring, well, everything else.
Exactly.
So where does that leave us? Do we have to choose a side?
I don't think so.
Yeah.
The future isn't about choosing one or the other. The real challenge is integration. How do we combine the incredible power of computational models, like the ones used in predictive processing, with the undeniable reality that human thinking is always tied to a body, in a place, using tools? That's synthesis. That's the next frontier.
Right.
And as fascinating as all the theory is, it's so important to remember why it matters. These shifts are happening because they have real practical urgency. They're giving us tools to understand education, mental health, and detraf, and even huge societal problems.
Absolutely. So to give you, our listener, the most actionable takeaways from this deep dive,
Right.
we've boiled it all down to 4 essential learning outcomes from the research. These are the things you need to know right now. Okay, number 1, educational insights. Cognitive science is now giving us concrete, evidence-based ways to learn better. The 2 biggest ones are spaced repetition and retrieval practice.
Spaced repetition is simple, really. Just spread your learning out over time instead of cramming. It works with how the brain naturally consolidates memory. And retrieval practice, which people often skip, is just self-testing. Forcing your brain to pull information out of memory makes that memory so much stronger than just passively rereading it.
These aren't just opinions, they're scientifically proven.
They really are.
Okay, number 2, the ethics of enhancement. The speed at which things like brain-computer interfaces, BCIs, are developing. It's forcing some really urgent ethical questions on us.
It is. Like, if we can enhance cognition, who gets access to that? You immediately have a social equity problem. But even deeper than that is the question of mental privacy. With neuroimaging getting better and better, we are getting closer to being able to decode what a person is thinking or intending to do just from their brain activity. Protecting your inner mental space is about to become a very real legal and practical issue.
Number 3, the hard problem. For all our progress, the massive gap between the brain's mechanics and our subjective experience, it's still the biggest challenge in the whole field.
We can map out exactly which neurons fire when you see the color red. We might even be able to predict your next thought based on brain activity. But we still can't explain why that specific pattern of firing feels like seeing red.
The redness of red.
Exactly. That gap between the objective brain process and the subjective phenomenal experience, that's the ultimate frontier for all of these models.
And finally, number 4, addressing societal challenges. We're now using what we know about the mind's flaws to help fix major global problems.
Yeah, understanding our cognitive biases is key here. Things like confirmation bias, our tendency to seek out information that we already agree with, or motivated reasoning. These are huge roadblocks to having rational conversations.
Especially about charged topics.
Especially then. So cognitive scientists are now designing interventions to help counter things like political polarization, or to frame a huge abstract problem like climate change in a way that feels more immediate and personal. We're using our knowledge of how the mind fails to build systems that help us succeed.
That is an incredible journey. From algorithms that challenge what it means to be creative, to a brain that's constantly trying to guess the future, and ending with the idea that your phone is literally a part of your mind.
And as we finish, just remember this. The more we learn about the mechanics of cognition, the more amazing and complex it all seems. Every new discovery doesn't take away the wonder of the mind. It just reveals deeper, more intricate layers of what it means to be human.
A perfect place to leave it.
So I'll leave you with one final thought to take with you. Which of the 3 big ideas we talked about today, the power of the computational revolution, the unifying promise of predictive processing, or the grounded reality of 4E cognition, which one most fundamentally changes how you think about your own mind and how you experience your world every single day? That's the question to explore as you continue your own deep dive.